Potential energy of an electric dipole in a uniform electric field. So in this figure we have these parallel lines, okay, represents the uniform electric field, and we have an electric dipole which consists of a charge minus q and plus q separated by a distance to a. Now this electric dipole here, it is placed inside the uniform electric field, and as we have seen before that when a dipole is placed in a uniform electric field, then the dipole will rotate in clockwise direction. So as the dipole rotates, then we have nothing but we call the moment of the mean, we have a torque. So this torque is given by tau is equals to Pe sin theta, where P here stands for electric dipole moment and E is the electric field, and theta is actually the angle in which this electric dipole makes with the electric field. Okay, so because the dipole in this case is able to rotate, right, like in this way, as the dipole rotate, then it changes its position, right? So if you remember in class 11 we have talked about potential energy. So potential energy is actually the energy which is associated by virtue of which a body is able to change its positions. Okay, so because a body like a dipole in this case, it is changing its position, so therefore this dipole will have a potential energy. Okay, so now how do we calculate the electric potential energy of an electric dipole when placed in such a uniform electric field? Okay, so now this is a torque, right, which is the rotating force. Okay, so therefore if the dipole in this case, let's say it is rotated through a small angle d theta against the torque, then when you rotate the dipole, okay, through a small angle d theta, then some work has to be done. Just like when you push a body, if you change the positions of a body from one place to another place, you need to apply a force. But in this case the force is not a linear force, but it is a rotating force, which is due to torque. So please remember here that torque is a rotating force, right? It behaves like a linear force only. So when you rotate the dipole through a small angle d theta, there should be a small work done, and that small work done is equals to dw. Just like work is equals to force into displacement. So in this case the small work will be force. Force is the rotating force, and instead of displacement we have the angular displacement. Why angular displacement? Because this dipole will not actually produce a linear displacement, but instead it is rotating, right? So as it rotates, that means there is a change in the angular a change in the position, or we can say there is an angular displacement. So this is the small work done to rotate the dipole through a small angle d theta. Now substituting the value of tau, that is Pe sin theta, so this will be the small work done to rotate the dipole through a small angle d theta. So therefore the total work done to rotate the dipole, right, let's say right from the positions when the angle is theta 1 to the positions when the angle is theta 2. So in that case the total work done is obtained by integrating the above equation. So if you integrate dw, you will get w. Now integrating this right hand side, you will get integrations, right, the limit is from theta 1 to theta 2, and then Pe sin theta. So this P and E are constant, so we take it outside the integration, and inside the integration you'll have only sin theta d theta. Okay, like I have shown it here. Okay, but integrations of sin theta is minus cos theta. So these are the limits of integration. And now taking this minus, right, put it here. So inside you will substitute the limits of integration. Instead of cos theta, then the upper limit is theta 2. I'll write cos theta 2, and then minus subtract with the lower limit, that is theta equal to theta 1. So this is, right, the work done. Or we can say W is equals to PE. Now I will insert this minus inside. So if you multiply this minus, then minus into minus will be plus. So cos theta 1 is positive, and minus into plus is minus. So cos theta 2 is negative. So this is actually the work done. Okay, to rotate the dipole from the positions theta 1 to theta 2. Okay, now let us suppose that theta 1 here is equals to 90 degree. That means the dipole, it is at right angles to the uniform field at the initial position, and let's say we rotate that dipole to a final position theta. That means in that case theta 2 is equals to theta, right? So therefore this equation 1 will becomes W is equals to PE. Instead of cos theta 1 I'll write cos 90, and then minus, instead of cos theta 2 I'll write cos theta. So W is equals to, we know cos 90 is 0, so we'll have only minus cos theta. So that minus I'll write it in front like this, so we'll get PE cos theta. So this is actually the work done to rotate the dipole from a position 90 degree to a position theta. So this work done, it's nothing but it will be stored right in the dipole as an electric potential energy, because we know work is nothing, it is an energy. So we get energy only by doing work. But what type of energy? It depends. If a body is changing its position, then the amount of work that you did to the body, that work will gain a potential energy. So therefore the potential energy of an electric dipole when placed in a uniform electric field, it is given by U, and U, it should be equals to this much. Okay, or we know PE cos theta is equals to P dot E, so therefore I will write U is equals to minus P dot E. Alright, so this is the required expressions for the potential energy of an electric dipole when placed in a uniform electric field. Okay, now let us look at the special cases. Number 1, when theta equals 0 degree, if you put theta equals 0 degree here, then cos 0 is 1, so you'll get U is equals to minus PE. So because of the presence of this minus, it means the potential energy of a dipole is minimum. Okay, now this minimum positions of the dipole means that it is, the dipole will be parallel to the electric field, and at the same time this position when theta is equals to 0 degree, it means it is a stable equilibrium position. Okay, second case is when theta equal 90 degree. When theta is equals to 90 degree, then substitute the value of theta here. Cos 90 is 0, so 0 into PE will be 0. So when theta is 90 degree, it means that when the dipole is held perpendicular to the electric field, then that dipole will not experience or will not be having any potential energy. Okay, will not be having any potential energy. Okay, the third case is when theta is equals to 180 degree, then U will be equals to minus PE cos 180. As we know, cos 180 is minus 1, so minus with this will become plus, so U is equals to PE. So because this factor here, right, it is positive, so we say this quantity is maximum. So thus the potential energy of a dipole is maximum when the dipole is placed anti-parallel, or we can say in other words, when the dipole moment, it is anti-parallel to the electric field. Okay, so that dipole will be having a maximum potential energy, and because of the energy is maximum, so we can say that this is the positions of an unstable equilibrium. So these are about the potential energy of an electric dipole when placed in a uniform electric field.